So yesterday we started talking about and went through a couple of the more standard arguments for why consistent theories, consistent meaning consistent with the principle of Lorentz invariance, locality, and unitarity of massless particles of spin greater than or equal to 1 are incredibly constrained at low energies. In fact, the structure of these theories at low energies is essentially, not just essentially, is uniquely determined. If you're going to have a collection of massless spin 1 particles, they have to be governed by a non-abelian gauge theory. Massless spin 2 particles have got to look like GR at long distances. Let me make a couple of comments. First, why do I keep saying long distances? In all of the arguments we're talking about in one place or the other, the amazingly constrained interactions are the leading, in a Lagrangian language, are the leading two derivative interactions. In the Weinberg theorem argument, again, they are the most leading interactions that involve the biggest power of this hard momentum in interacting with the soft particle. So nothing stops you, especially in a Lagrangian language, from imagining adding lots of higher dimension operators, but they're all irrelevant at long distances. The leading two derivative interactions are the things that are completely nailed by general principles. So it's a very beautiful picture. There's no choice but for the world to look like the way it looks at long distances. It's not some thing of aesthetic beauty. If we have these massless particles at long distances, this is the only possible way that we could describe them. Now, one thing I perhaps should have emphasized yesterday, but yes?
So with the spin 1 particles, were it free to choose any gauge group?
Right.
What was it that made the gauge group fixed for the spin 2 particles? Fixed as the diffeomorphism?
Well, because even at the very, very start, the structure of the redundancy that you needed for spin 2 was different than spin 1. Okay? And so this is something I could have also, maybe I didn't say it yesterday. So we saw, even at this first most linearized level, that the sort of redundancy you needed for spin 2 involved this p mu alpha nu plus p nu alpha nu, right? Now, and then we saw that the only invariant that you could build out of it looked like the linearized Riemann tensor. Now, let's say you'd never heard of the Riemann tensor, you'd never heard about all this geometry. Is it shocking? Is it a complete coincidence that the linearized Riemann tensor makes an appearance? No, of course not. It's because already the redundancy that you need for the massless spin 2 particle, you can recognize as being a linearized diffeomorphism. Okay? So it's not shocking then that it nonlinearly completes as something which is the full diffeomorphisms. Okay?
Why do you use the freedom?
Oh, it's not freedom. It's just that spin 2 meant h mu nu. It had two indices, so its redundancy was different than for spin 1. That's all. So they're both local gauge symmetries, but they're very different. One of them is well, they're both local symmetries. One of them is diffeomorphism. The other one's gauge symmetries. Yeah. So something else I should have emphasized is that all of these arguments. It's important that there's some weak coupling around. This is important for many reasons, and often people think that there's something bad about weakly coupled theories, or you're somehow talking not generally enough, and you should do everything fully nonlinearly, and so on. And this is obviously silly for one reason. Even if something very nonlinear is going on, you better understand what's going on at linearized level or close to linearized level first. Not doing that, I think a nice analogy I've heard is that not doing that is trying to learn differential geometry without knowing linear algebra first, okay, which is clearly a silly thing. But even more than that, even having the observables, even the names we give these things, always have implicitly in the back of our mind some weakly coupled description. For example, when I say I have massless spin 1 particles, massless spin 2 particles, the very name is assuming that these asymptotic states exist that I can identify. I can measure their spin. I can see what it is, right? So whatever's going on, the interactions can't be so horrendously strong that they stop you from having these guys as asymptotic states. Fortunately, for the case of gravity, there's always guaranteed to be a regime where it's weakly coupled because the coupling is dimensionful. At energies small compared to the Planck length, compared to the Planck scale, the interactions for gravitons are bound to be weak. It's not guaranteed in the case where we have dimensionless interactions, like we talked about for gluons. And you might object that we certainly know lots of strongly coupled theories. We know lots of observables, other observables in strongly coupled theories. You know, we can have some conformal field theory at strong coupling, and we talk about correlation functions between local observables. But always, always, in the back of our mind, there is something weakly coupled there. When you measure some correlation function, let's say you want to measure the correlation function of the energy momentum tensor, really what you're doing is imagining weakly coupling this whole theory to gravity, and you're measuring some property to do with, or you could extract that correlation function from some property of the gravitational amplitudes. Or, of course, more normally, we don't actually measure energy momentum correlation functions using gravitons, but you have some device, some apparatus which has some, which flashes red or blue or something where the photons come out. You know, things are weakly coupled at the end, and it couples to the thing that you're trying to make some measurement of. Okay? So there's always something in the back of every one of these observables, even the ones that we talk about in strongly coupled theories. The way you actually extract them involves something weakly coupled, something that can be approximated as a weakly coupled scattering amplitude deep down the line somewhere. Okay, and the other thing that I emphasized is that to make locality manifest in our description of these massless high spin particles of spin greater than or equal to 1, the only way we could do it, we had to assemble these guys into fields. We wanted to write down local interactions for these fields, and the only way to do it was to introduce these gauge redundancies. So I just want to spend one moment here. I mean, it's a theme that's going to come out again and again in the rest of these lectures. But to just explicitly address what you might feel as a sort of tension here. On the one hand, I keep saying these gauge redundancies are totally meaningless things. They're just a language. They're up to us. The real physics is the fact that you have these massless spin 2 particles. There's no invariant content in gauge symmetry or diffeomorphism invariance in itself. And we'll see this big time, because we'll take theories that look crappy, non-gauge invariant, non-diffeomorphism invariant theories, and we'll express them and write them in a way that is diffeomorphism invariant and gauge invariant. And you'll see very explicitly there's no actual content purely to the statement of the existence of general covariance or the existence of gauge invariance. How does that square away with what you all know and what you've all learned, which is that it's damn hard to make gauge theories, right? And that if you try to make a gauge theory for non-abelian gauge theories or generally covariant field theories, that it's incredibly constrained and you have to invent all these incredible Christoffel symbols and Riemann tensors and gauge connections and curvatures and all of that stuff. So how can it be that this thing, which has so much structure in it, is content-free? So the real point is that the actual existence of the gauge symmetries is content-free. However, realizing, in trying to write down a Lagrangian, realizing these gauge symmetries on precisely the degrees of freedom that you're interested in, and no other degrees of freedom, is the incredibly challenging part. Okay? So if you want to describe massless spin 1 particles and nothing else, not secretly some spin 0 components, not secretly some other crappy components, just the massless spin 1 particles and nothing else. Well, to do that, using a gauge redundancy, the redundancy is so strong it uniquely fixes the form of the Lagrangian. Okay? That shouldn't surprise you, because from the other side, what I told you yesterday, totally ignoring any formalism for describing it, the actual physics, long-distance physics, the actual amplitudes for how these guys interact is actually completely determined by unitarity and Poincare invariance. So it shouldn't shock you that if you're going to try to introduce some technical tool, useful tool to describe it in a Lagrangian form, that way of doing it will be incredibly constrained and force you into a unique structure. But we'll see, and all attempts to modify either gauge theory or gravity involve adding extra degrees of freedom. And then we'll see very, very explicitly how the issue is not general covariance, is not gauge invariance. That part is trivial. What's non-trivial is describing the degrees of freedom that we want, And furthermore, when we modify these theories, what's non-trivial is keeping control over the extra degrees of freedom that are inevitably being introduced. Okay? But there's no contradiction, right? So if you're only going to describe, if you only want to describe the mass of spin 1 or the mass of spin 2 particles using diffeomorphism redundancy or gauge redundancy, then those are amazingly powerful, incredibly useful tools and completely nail the structure of the Lagrangian. They will most certainly not completely nail the structure of the Lagrangian once extra degrees of freedom are allowed, as we'll see. Okay, but what I want to do today is to start off with is something which I wanted to do last time, but is the promised sort of third way of understanding why these theories are so constrained at long distances. And this third way is, in a sense, the most airtight of all of them. In both of the other ways that we were describing things, somewhere we're putting in some assumption about how we're going to describe the physics. I mean, completely, totally reasonable things. We're going to write down Lagrangians. Or even in the Weinberg argument, even though it looks like it was a little more independent of that, we're talking about explicitly this physical thing, the amplitude for the soft emission, for the emission of a soft particle. Still, in computing it, we had some picture that there was a tree diagram. We were working in some tree approximation. Again, this is important because, as I mentioned, all these arguments involve some weak coupling, so we're looking at it in leading order and some weak couplings. So they still have some tiny whiff of a dependence on formalism on them. So I want to give you a sort of third argument, which I think is the sort of most invariant argument of all. But to do this, what we're going to do is actually, instead of abstractly imagining what these are, we're just actually just going to write them down. Okay? So I want to start off telling you how to think about the scattering amplitude for massless particles. Now, what do I mean we're just going to write them down? Well, the entire discussion yesterday was all predicated on the assumption that we were computing, the actual amplitude depends on the helicities of these particles and depends on the external momenta. This is the actual physical real amplitude, right? It just depends on the external helicities and the momenta. But we're assuming that the way that we were computing this, implicitly assuming, just in the whole way we set the entire problem up, that we're computing it not, you see, this amplitude doesn't have any Lorentz indices. It only has helicity indices, okay? But what we do when we compute anything that looks like Feynman diagrams is compute things, let's say we're doing spin 1, that has a bunch of Lorentz indices, and then we say that we're going to get the actual amplitude by dotting this into polarization vectors. So this way of thinking about what the amplitude is a function of, this is a function of the polarization vectors and the momenta for each particle. But as I stressed yesterday, and this is the origin of all of the constraints, there is no such thing as the polarization vector. It's redundant. It has this redundancy built into it. And it's making sure that redundancy is redundant, which is where all the constraints come from. Okay? But it also means that you have not seen in a course, if you've seen an amplitude presented in this way, you've actually not seen an actual scattering amplitude. You're always seeing it presented in some redundant form. You're not seeing what the actual object is. Okay. So let's figure out how to talk about what the actual object is. All right. Now, I could spend a little longer explaining this part in detail, but let me cut to the chase a little bit. In order to see what the amplitudes are actually directly a function of, it's useful to introduce a new set of variables for describing massless particles. So normally when we have a massless if we have some massless guy, we're content to describe it in terms of a 4-vector, but the 4-vector satisfies a constraint, right? That the p0 squared is equal to the magnitude of p vector squared. So it's a little annoying having this nonlinear constraint on the p's. So for the moment, just for fun, and we'll see what the sort of deep point of these variables are in a moment, but for the moment, just for fun, it's useful to introduce a new set of variables which are not constrained. You just give these variables, and it automatically builds for you a 4-vector which is null. Okay. To do that, we're going to imagine dotting the p's into a bunch of Pauli matrices. If you haven't seen this notation, don't worry so much about it. These are Pauli matrices are 2x2 matrices, and just for fun, we are describing one of the indices as A, and the other indices as A dot. So A and A dot run from 1 to 2, but these sigma mu's explicitly are just 1 on the Pauli spin matrix. And so very explicitly, this matrix is P0 plus P3, P0 minus P3, P1 plus IP2, P1 minus IP2. Okay. So you see this is a 2x2 traceless Hermitian matrix. Sorry, not traceless, just a 2x2 Hermitian matrix. Okay. In fact, if I handed you a random 2x2 Hermitian matrix, you could read off from it the components of some 4-vector P. You'll also notice that the determinant of this matrix, so let's call this matrix PAA dot. The determinant of PAA dot is just P0 squared minus P3 squared minus P1 squared minus P2 squared. So this is just P mu, P mu. Okay. So that's nice. The determinant of this matrix is just P squared. And that means that there's a way of realizing Lorentz transformations on this 2x2 matrix. Okay? If you do any complex linear transformation you like on this 2x2 matrix, if you take it to L inverse this matrix times L, where L is any 2x2 linear transformation of unit determinant, then you'll find that the determinant of this matrix is, of course, invariant. Okay? So if I take P sigma dot P goes to L sigma dot P, L inverse L, then det sigma dot P goes to det sigma dot P, so long as det L is 1. And L can be a completely random complex 2x2 matrix. That preserves the fact that this will be a 2x2 Hermitian matrix. Okay. So this gives you a representation of Lorentz transformations. And it's the Spinor representation of Lorentz transformations. Okay. Okay. But for our purpose, we're going to use this to make a little observation that if I take this 2x2 matrix, if P is null, then P squared is 0. And if P squared is 0, this determinant has 0 determinant. This determinant has a vanishing eigenvalue. So it's either 0 or it has rank 1. If it has rank 1, you can just build it out of the outer product of a 2-vector and some other 2-vector. Okay, so I could write P A dot. I should be able to write as some lambda A times some lambda tilde a dot. This guarantees that the determinant of p is equal to 0. So p squared equals 0 means that p can be written in this way. Now, part of the point of using these two different, of this A index and the A dot index, is you can plainly see just from how Lorentz transformations are acting as this L inverse sigma dot BL, that the Lorentz group just acts as 2 by 2 linear transformations just on this two-dimensional vector lambda, and the complex conjugate of that on this two-dimensional vector lambda tilde. Okay? Now, without apology and without too much explanation, we're going to actually imagine that everything is complex for the rest of this, lecture. So actually, the completely complexified Lorentz group is 2 copies of a general. I can do totally general SL. I can do totally general 2 by 2 complex linear transformations of determinant 1, a separate one on lambda and a separate one on lambda tilde. Okay? So that's the reason for having these different indices. If we're describing real momenta, that matrix P had better be Hermitian. So for real momenta, lambda tilde has got to equal lambda star, really the complex conjugate. But if the momenta are complex in general, then the lambda and lambda tilde can be treated as 2 independent complex parameters. If you want to describe a real momenta, they have to be identified with each other. Okay, so you see, as promised, instead of giving you some 4-dimensional vector and forcing by hand that the time component be equal in magnitude to the space component, I instead hand you a lambda and a lambda tilde. You just take the outer product, and that guarantees that it's going to give you a null vector. So these are now unconstrained variables. Oh, but there's something a little confusing. The p's, there's 4 p's. There's 1 constraint, so there's 3 degrees of freedom in the p's. But it looks like I have 2 degrees of freedom in lambda, 2 degrees of freedom in lambda tilde, so there's 4 degrees of freedom again. So what's going on? Well, what's going on is that while this p is guaranteed to be null, the lambda and the lambda tilde are not unique. Clearly, I can take lambda and rescale it by some t lambda, and lambda tilde and rescale it by t inverse lambda tilde, and that's going to leave p invariant. Okay? If, for real momenta, t would have to be a phase, okay, in order for these things to remain complex conjugates to each other. So for real momenta, what we're saying is that the lambda and lambda tilde are not defined uniquely, but I can rephase them arbitrarily and keep this null momentum fixed. Okay. But that's really, really nice, because the transformations which leave the, so here I have a momentum, some null momentum pointing in this direction. How would we know what the helicity of the particle is? Okay? The helicity of the particle is completely determined by how the amplitude behaves under those transformations that leave the momentum fixed but just do a rotation around the direction of motion, right? That's what helicity is. So this freedom is precisely reflecting that helicity transformation. We could say this all a little more precisely using the language of the little group and so on, but it's intuitively very, very clear. So that means that I can give a, if I'm talking about the amplitudes for massless particles, I can now write them directly in terms of these variables lambda and lambda tilde. Not redundantly in terms of momenta and polarization vectors, but directly in terms of lambda and lambda tilde. In fact, I don't need, that was one of the funny things before. You had momenta and these polarization vectors. Here there's one set of variables, the lambdas and the lambda tildes directly. But now I'll tell you how the helicity is encoded. So this is a function of the lambda I and the lambda tilde I for all of the particles. But this function, whatever it is, it has to have a certain homogeneity, a certain scaling when I scale the lambda and the lambda tilde in this way. And that scaling is telling us what the helicities of the particles are. So explicitly, it's that m of h1 up to hn, if I rescale each lambda I by ti and the lambda tilde I by ti inverse, then this goes like ti to the power of negative 2hi times m of lambda I and lambda tilde I. It has to have a certain overall weight under rescaling any lambda and lambda tilde individually. And what the weight is tells you precisely what the helicity of the particle is. So this negative 2hi is a conventional. Why is there a 2 there? It's because so the lambdas are like the spin a half representation. So we see what happens to lambdas is lambdas just pick up a single factor of t. Okay? So this rephasing for a spin a half particle would just be t or e to the I theta. So if it's got spin h, it'll be e to the I, it'll be h times that. And so that's where the t to the 2h comes from. When h equals a half, it should be 1. And it's just purely conventional to put the minus sign there. All right, let me say this a little more concretely. Here is an example of a scattering amplitude for 4 spin 1 particles. I'm doing this just to illustrate. This is a very, very special amplitude. They're not all this simple. But it's just to illustrate what I mean by it. Oh, sorry. Before I do that, I should have said one more very important thing. Apologies. So remember, the Lorentz group is just acting as 2 by 2 linear transformations on this guy and that guy. So the only invariance that we can have, the only Lorentz invariance that we can have, made out of these lambdas and lambda tildes, just contract the lambdas together or the lambdas together or the lambda tildes together using the epsilon tensor. So again, the Lorentz transformations are this. So L det L is 1. We also have some lambda tilde alpha dot or A. Sorry, that's what I was calling them. So there are two different 2 by 2 linear transformations. The only things that are invariant under these transformations are the 2 by 2 antisymmetric tensors. So the kinds of invariants that I can talk about are things like epsilon AB, lambda 1A, lambda 2B, for example. If I have 2 different ones. If I have the same one, I contract them together, I get 0. If I have 2 different ones, I can have something like that. So this is often abbreviated as angle bracket 1, 2. Similarly, I can contract things for this guy, and that's abbreviated as square bracket 1, 2. Okay? So whenever you see these angle brackets, it's made out of lambdas. Square brackets is made out of lambda tildes. So you see, this is some incredibly special amplitude. It's only made out of lambdas for some reason. I won't spend any time talking about it, but I just want you to see exactly what I mean. Okay? So this is an amplitude. It's built out of these Spinor helicity variables, just built out of the lambdas. It's manifestly Lorentz invariant, because I've built it out of Lorentz invariant things. However, I can also read off from it what the helicities of the particles are. Because while it's Lorentz invariant, it's not invariant, for example, under rescaling 1. If I take lambda 1 and I extend it to T1 lambda 1, this whole amplitude, m, goes like, well, I get 4 1s upstairs. I have 2 1s downstairs. So the amplitude goes like t squared, t1 squared, m. The amplitude is not invariant, but that's good. In fact, its non-invariance is precisely telling us the helicity of particle 1. And from here, I conclude that's equal to negative 2h1, I conclude that the helicity of particle 1 is equal to minus 1. Okay? So there it is. Indeed, it's a particle of spin 1 with negative helicity. Okay? And you can do this similar exercise for the remaining guys. Okay? So amplitudes are not, they're redundantly functions of polarization vectors and momenta, but they're directly functions of spinor helicity variables, amplitudes for massless particles. These lambdas and lambda tildes are known as spinor helicity variables. And so we see they're directly functions of lambda and lambda tilde. And the helicity information is contained in the homogeneity in how these amplitudes scale under doing this transformation, which leaves the momentum invariant but rephases lambda and lambda tilde. Okay? So now, if you haven't seen it before, now you've finally seen an actual amplitude. That's an actual amplitude. Okay. Yeah, there's some constant in front of it, right? No, there's no constant there. That's just the definition of how it transforms. There's some constant in front here. Now, this has a nice consequence. It means that it's very easy to just make ansatzes and make guesses for what something that might be an amplitude looks like, which is completely consistent, at least at the level of having the correct transformation properties. You just build anything built out of these lambdas and lambda tildes that has the correct homogeneity, it begins to have a right to be called an amplitude. Okay? At least it has all the correct transformation properties and everything. You see, from this point of view, we're starting from the opposite side that we're starting from yesterday. Here, using these variables, from the get-go, we're going to be guaranteed to be talking about things that are Lorentz invariant. Okay? Last time, from the get-go, we were guaranteed to be talking about things that were local and unitary, but then we had to check Lorentz invariance, because under Lorentz transformation, polarization vectors didn't transform like blah, blah, blah. So the way the constraints are going to be seen is going to be rather different. Here we're starting from the opposite starting point. We're starting with things that, for a fact, no doubt, are allowed to be called, past the first check to be called amplitudes. And then we're going to see that they're going to have to satisfy very, very strong constraints. Yes?
What we can write down looking at the unit?
Yeah, there's a gigantic number of things we can write down. Absolutely, absolutely. No. They have to satisfy many more physical constraints. In fact, we have to, again, we're starting from the opposite side. So we're hardwiring in the correct Lorentz invariant description. Now we have to check unitarity. Okay? Before, we were hardwiring in the particles, unitarity, and we had to check that it was actually Lorentz invariant. Okay? But this has an advantage that no matter what formalism you use, no matter how you do it, in the end of the day, you will have to produce a formula that looks like that, because this is what amplitudes are actually functions of. Okay, so it's a little bit more, yeah. Okay, so let me give you, so let's start off seeing what incredibly powerful constraints there are by talking about a very simple object. We're going to talk about the 3-particle amplitude. Yes? No. Everything is going, because the Lorentz group is 2 separate SL2s acting on lambda and lambda tilde. Okay. Now, the 3-particle amplitude is not something you normally talk about in courses. In fact, it's always something that might have bugged you a little bit, because it's completely clear, certainly when you stare at Lagrangians for gauge theory or gravity, that the 3-particle vertex is somehow the most important vertex. It's always there. The other ones are sort of slaves to it. You have a coupling G. Okay, in gauge theory, there's a quarter coupling, but that's G squared. So this 3-point coupling seems like the most primitive thing. And yet we never talk about the 3-particle amplitude. There's a good reason we don't talk about the 3-particle amplitude, and that's because it's 0. It's 0 for real momenta, and it's 0 for real momenta for many reasons, but the basic problem is we have massless particles. You can't have a massless particle split into two other massless particles, conserving energy and momentum, unless the two particles that it's splitting into are dead exactly collinear with the direction that the first one is going in. So it's a very, very singular process, and so that's why we don't normally talk about it. However, it turns out that that's an accident of working with real momenta. And if we allow the momenta to be complex, just as a formal device for the moment, we'll be able to talk about even three-particle amplitudes in general. Okay. So in order to see that, let's actually see what so we saw that the first funny constraint has to do with how energy and momentum conservation work. So let's see what energy and momentum conservation means for three particles. Okay? So 1, 2, 3. Actually, before doing anything, let me do something even a little more naive. Normally, since we'll be talking about four particles in a moment, let me just remind you something perhaps slightly more familiar in four particles. So if we have four particle scattering, even ignoring the helicities for a second, and this is momentum P1, P2, P3, and P4, then we can have all sorts of Lorentz invariants. Like P1.P2 is a Lorentz invariant. Okay? Well, this is equal to P3.P4 by momentum conservation. In fact, since we know P1 plus P2 plus P3 plus P4 squared is 0, we can conclude that all the P1.P2 plus P1.P3 plus P1.P4 is equal to 0. Sorry, I'm writing so badly with this chalk. And these things are sometimes given, and here I use that p squareds are equal to 0. Okay? So these things are normally given names. They're the Mandelstam variables s, t, and u, and we see from here that s plus t plus u is equal to 0. But so there's a ton of Lorentz invariants that we can use to characterize the scattering process. Okay? So four particle amplitudes could be very complicated things in principle. They could be functions of s, t, and u. But let's just think for a second, what could the three-particle amplitude possibly be a function of? And you see that all of these things are absent, right? Can I have P1.P2? Nope, P1.P2 is 0. Okay? P1.P2 is 0 because this is equal to P1 by momentum conservation, negative P1, negative P3. And sorry, I should have said it better. So P1.P2 is 2P1.P2 is also P1 plus P2 squared, because P1 squared and P2 squared is 0. But this is equal to P3 squared and is 0. Okay? So P1.P2 is 0. All the Pi.Pj's are 0. So there are no kinematic invariants associated with this guy. That's good, because it tells you that whatever it is, it's pure helicity information and nothing else. Okay? And it gives you the first hint that this three-particle amplitude is going to be completely determined just if you specify what the helicities of the external particles are. Okay? So we don't have the analog of ST and U for three particles. All right, but now let's get to the business of studying this in a little bit of detail. So I want to see what momentum conservation implies on these lambdas. So momentum conservation is a statement that P1 A dot plus P2 A dot plus P3 A dot is equal to 0. Or that lambda 1, lambda tilde 1 A dot plus lambda 2, lambda tilde 2 A dot plus lambda 3, lambda tilde 3 A dot is equal to 0. Okay? All right. Now, it's very important that these lambdas and the lambda tildes are two-dimensional vectors. Okay? So this is going to be important a number of times. But let's just begin to get an idea of what this implies. Let's say I take this equation and I multiply by lambda 1, let's say, by lambda 1b. So I'm going to multiply by lambda 1b and contract with an epsilon ab. Okay? So we will refer to this as just as contract with lambda 1. So we'll contract with lambda 1. And if we do that, we see something very simple immediately. We see that 1, 2, lambda tilde 2, plus 1, 3, lambda tilde 3 is equal to 0. Okay? Now, let's just assume for a second. So if we look at this formula, and if we assume that 1, 2 is not equal to 0, okay? 1, 2 is not equal to 0. The coefficient of this vector is not equal to 0. Okay? But then we learn something interesting. We learn that, now, let's say that 1, 3 was 0. If 1, 3 was 0, then that's forcing lambda tilde 2 to just vanish. If lambda tilde 2 vanishes, P2 just vanishes. And that's too singular. So we're not interested in that. We want some non-zero momenta. Okay? So we don't want to set any of them to 0. So if 1, 2 is not equal to 0, 1, 3 it also better not equal to 0. Okay? So 1, 2 and 1, 3 are both not equal to 0. But then we learn something interesting, that lambda tilde 2 and lambda tilde 3 are proportional to each other. So there's two-dimensional vectors that are proportional to each other. Since they're proportional to each other, if I contract them with an epsilon symbol, I'm going to get 0. Okay? So from here I learn that 2, 3 is equal to 0. And I'll leave it as a tiny exercise for you. Well, we could just do one more step, but I'll just leave it anyway. To show that actually the only way to satisfy momentum conservation is so momentum conservation tells us that either all the ij's are equal to 0, or all the angle brackets are equal to 0. And then the ones that are not, and ij generic, and here the other way around. These ij's generic. Okay. So that's what momentum conservation implies. Either the angle brackets vanish or the square brackets vanish, and the other ones don't. Now you see from here immediately why we don't see this for generic momenta, why we don't see this for real momenta. Because for real momenta, the angle brackets are the complex conjugate of the square brackets, so I can't set one to 0 without setting the other one to 0. That's why for real momenta, we don't see this. But for complex momenta, we do. We're allowed to have these things be independent, and so we can have this. Now, this is amazingly powerful because now, perhaps I should have said something even this board, which is now, oh boy, too many things hidden. Let me just put it here. So if we take something like P1 dot P2, what is P1 dot P2? Well, you can easily see this is lambda 1. You can very easily see this is just angle bracket 1, 2, square bracket 1, 2. Okay? Because it has to be lambda 1, lambda tilde 1, contracted with lambda 2, lambda tilde 2. So only the 1 and 2 can go together, and the 1 tilde and 2 tilde can go together. So this is very nice because, remember, these momenta themselves were totally invariant under this Helicity transformation. Lambda goes to T lambda. Okay? So anything which has helicity 0, well, so P1.P2 is helicity 0, so that's good. We have 2 and its conjugate here, 1 and its conjugate on the other side, so that thing has helicity 0. And so when we have these helicity-free objects, like these kinematic invariants, we can imagine, as we did for 4 particles, incredibly complicated functions. Okay? And in fact, the ratio of P1.P2 to P1.P3 is even dimensionless. So we can raise it to arbitrary powers and imagine that it's there in the amplitude somewhere, just on general grounds. Okay? So you can have incredibly complicated functions. However, this can't happen if the amplitudes are only functions of the lambdas or only functions of the lambda tildes. Okay? The thing that's the source of all the complexity, all these kinematic invariants, are these things of helicity 0 that you can build putting both of them together. But we see for the 3-particle amplitude, these things don't exist. Well, we saw it even to begin with on the left, but we now see, again, these kinematic invariants are built out of products of angle and square brackets, and they all vanish. Okay, so that means that if I'm going to write a 3-particle amplitude, I can either only use angle brackets or only use square brackets. So let's do it. Let's do it for general spins. So imagine this is spin negative S1, spin negative S2, helicity, and helicity negative S3. The negatives, they're just there to make my life a little easier. Okay. This is particle 1, 2, and 3. And let's say we're going to try to write this down purely in terms of angle brackets. Well, all we can do is write down 1, 2 to some power. So let me write down 1, 2 to the A3. I can write down 2, 3 to some power. And I can write 3, 1 to some power. And I can write down some constant. Okay, but these powers can't be arbitrary. Remember, this thing has to have the correct helicity. So we're going to just determine these powers, A1, A2, A3, just by matching what these spins are. So under rescaling 1, the amplitude picks up a factor of A2 plus A3. So we learned that we have to have A2 plus A3 is equal to negative 2s. So that's 2s1. And similarly, cyclically. So we have to have A3 plus A1 is 2s2, and A1 plus A2 is 2s3. So then I can solve for all the a's. So let me solve for A1 by adding these 2 equations. And, well, add 2 of them and subtract the third. And so, for example, so I can solve for A3, and I find that, that A3 is equal to S1 plus S2 minus S3. Okay. So if I add these 2 equations and subtract that one and divide by 2, I get that's A3, and similarly for the other ones. So A2 is S3 plus S1 minus S2, and A1 is S2 plus S3 minus S1. So that's remarkable. That completely nails what this amplitude can look like. Okay. We've totally, up to a constant, it's completely fixed just by Poincare invariance. Okay. Nothing else. Now, this was the case where I only used angle brackets. If I only use square brackets, I would get exactly the same formula, but just reversing all the signs, right? Because the square bracket guys have opposite helicities. So now comes an interesting. So that's what the formula is for a general. And by the way, it's also just very easy to remember. So you look at this picture, and the power of 1, 2 is just that spin plus that spin minus the other one, and so on. Okay? Just rephrasing the formula. Okay. So let's just write down some concrete examples, ones that will be particularly relevant to us. It is not. That's just what I'm about to talk about. So let's say the particles all have overall spin s. And I'm looking at configurations where 2 are minus and 1 is plus. Okay? Then this thing would be 1, 2 cubed. That formula just turns a 1, 2 cubed over 1, 3, 2, 3 to the power of s. This is 1, 2, and 3. So we can see that, again, it makes sense because we have 3 1s upstairs, 1 1 downstairs, so a total of 2 1s upstairs, so that we get 2s upstairs, and that's exactly what we mean by having spin minus s, or helicity minus s. Okay? Okay, so it could be a constant. And as Matthias was saying, we could also have 1 2 cubed over 1 3 2 3 to the negative s, some constant prime. And now comes one final physical requirement. Okay? The physical requirement is that whatever this amplitude is should be smooth in the limit as I go to real momenta. It shouldn't blow up when we go to real momenta. It should be smooth in the limit when we have real momenta. Real momenta, remember, is the limit where the angle brackets are just the complex conjugate of the square brackets. So when I have this term, I'm imagining that all the angle brackets are 0. When I have this term, I'm imagining all the square brackets are 0, and here all the angle brackets are 0. So now as I take the limit where the momenta are real, that means that I also have to, for example, up here, I have to make the angle brackets also 0. Okay? You see, if I make this choice, then the amplitude is smooth. Of course, these are going to 0, but that's going to 0 faster. There's 3 powers upstairs and 2 downstairs. So this is smooth and actually goes to 0 in the limit of real momenta. Yeah.
So if all the particles are massless here,
yes.
Is the Fourier transform with the usual statement that in conformal field theory we go to 3-point function?
Yes, it's precisely, and it's exactly the same argument. Yes, it's exactly the same argument. And the formula is very familiar. Okay? It's exactly the same formula. Well, I mean, it's not literally the Fourier transform, but it's essentially exactly the same argument. Okay? Essentially exactly the same argument. In both cases, they're completely determined by a symmetry. Here it's completely determined by a Poincare symmetry. There it's completely determined by a conformal symmetry. But it's well, no, that's not true. Gravity isn't conformally invariant. We'll be talking about gravity. So it's yeah. So it's but it's a very similar argument. It's a very, very similar argument. Okay. Now, on the other hand, if we take this guy, and the limit as we take the momenta to be real, this guy would blow up. Okay? So for this configuration, that's why we drop that coefficient, and so we have this. This result for the case of all. So when it's minus minus plus, it looks like that. And when it's plus plus minus, the amplitude would then be the one with the angle brackets. Okay. Well, we'll have to remember that formula. I'll write it down when we need it again. Okay. By the way, that's what about the other configurations? So that we did with 2 plus and 1 minus. What about the amplitude where all 3 are minus, say? Can we have one where all 3 are minus? And let's say, again, they're all spin s. I mean, we wrote down the general formula, but just so we take a look. Here, it would be 1, 2, 2, 3, 3, 1 to the power of s. Okay? And if it's all plus, it would be 1, 2, 2, 3, 3, 1 to the power of s. So let's just pause for a moment. First of all, you see something interesting. That there's a difference between these two amplitudes. Not only do they look different, they have different units. Okay? This has some extra guys downstairs than this guy. So if we're going to, we know the physical dimension of these amplitudes. For the physical dimension to be the same, these guys have got to be suppressed by some extra powers of some mass scale relative to these guys. Okay? So these are the leading interactions. They're the leading interactions at low energies. These are subleading. They're really different interactions. Secondly, let's just stare at some of them. So, I mean, it's silly because we wrote the formula, but just for spin 1 particles, okay? So this basic 3-point amplitude is just 1, 2 cubed over 1, 3, 2, 3 with minus, minus, plus. So that's an amplitude for gluons. If we look at this interaction for spin 2, it's just 1, 2 cubed over 1, 3, 2, 3 all squared. Okay. So first of all, you see something quite beautiful, that the 3-particle amplitude for gravity is the square of the 3-particle amplitude for Yang-Mills. We can read off the dimensions. So again, we know the physical dimension of the 3-point amplitude. So this guy is dimensionless, whereas this guy has to have coefficients of 1 over a mass that we can call 1 over m Planck. Okay. And thirdly, of course, these are the 3-point functions that you would get if you took the Yang-Mills Lagrangian and plugged in the polarization vectors into the 3-point function. Of course, that's what you'd get if you did the calculation. Yang-Mills is not so bad. It's still not as simple as just writing it down. And we don't appreciate that it's completely nailed by Poincare symmetry, but you can do it. Now, you can also do it for gravity, but it gets considerably more complicated. The actual 3-point vertex, if you gauge fix linearized gravity in some normal gauge, has 80 terms in it. So it's a pretty long calculation. But of course, dutifully, at the end of the calculation, you'll of course get exactly that. Because it doesn't matter what the Lagrangian looks like, doesn't matter anything. It's completely determined by Poincare invariance. Okay, so as I promised, these are the leading things at long distances. What are these funny guys? These guys correspond to what you could add that would give you 3-point interactions as higher dimension operators. So if you added something that went like f mu nu cubed in Yang-Mills theory, you'd get this guy. Or if you added something that goes like r cubed in gravity, you'd get the other, you'd get the other guys. Okay? So, but we also learned something. Simply as far as the 3-point interaction goes, this is all the structures you can possibly get. And furthermore, they can't at all be renormalized. Okay? The structure is determined up to a constant, and there's no renormalization of these things of any sort. Yes, you had a question.
Yeah, so just a question. So does this mean that these amplitudes include all possible quantum corrections?
Everything. They can't be anything else. Okay? They can't be anything else. Okay. Yeah, I mean, implicitly, unitarity, well, we've used a very bare version of it, which is that the external particles have got to be labeled by helicities. Okay? That's very fancily a consequence of unitarity, but it's not the real juice. The juice of unitarity is what we're about to come to when we talk about the consistency of 4-point functions. And it's that the fact that unitarity then comes in from the fact that when you have 4-point functions, well, we're about to talk about it, when you have 4-point functions and they have poles, the poles need to have an interpretation. The residues of the poles have to be interpreted as factorizing to the product of lower point amplitudes. And that's where we're going to get the constraints. Here, what you've learned is that simply at the level of a 3-point function, there's no obstruction to writing down an interaction for anything. Okay? Spin 17, no problem. These things are completely nailed by Poincare invariance. But you also get the sense for how powerful Poincare invariance is, even at this basic level. All right. But now the fun is going to begin. Now what I want to do is show you that the only consistent theory, sorry, I should have said one more thing here. One more thing. Notice that from here we can also read off the statistics. Okay? So this expression might look a little surprising to you. You see, if I interchange 1 and 2, that expression picks up a minus sign, because it's antisymmetric in 1 and 2. These angle brackets are antisymmetric. They're built out of contractions with the epsilon symbol. Okay? This guy, on the other hand, is perfectly fine, right? It's just, by the way, what would phi cubed theory be? Just scalars. What would the 3-point function be? Easy question. Just a constant, right? So just a total constant. But so this is funny because it looks like the only possible consistent interaction we could have for a massless spin 1 particle would pick up a minus sign under interchanging them. That seems to violate both statistics. Okay? It seems to have Fermi statistics. Now, if I had a lot more time, I would tell you how to derive the spin statistics connection and all the other stuff like that from similar considerations. But for now, let's assume that that we believe the spin statistics connection from somewhere else. So this actually tells us that there's no way I could have such a self-interaction for a single spin 1 particle. Okay? And in fact, there is no such self-interaction for a single spin 1 particle. Okay? The only way to have those self-interactions is if we have many spin 1 particles. So if I label this with an A, B, and a C, the only way that we could then make the statistics work out is if this coupling is an F ABC, which is completely antisymmetric in A, B, and C. Okay? So, and that tells you, without even thinking about it, no U1 theory just of photons ever is there any physical 3-point coupling. Okay? On the other hand, no such restricting for a single spin spin 2 particle. So it tells us if we're going to talk about theories of single spin S particles, and for the moment we're just going to spend a few minutes just talking about that, we should only consider even spins, right? So we're going to spin 0, spin 2, spin 4, and so on. Okay. So now what I want to do is show you that the only consistent theories of a single self-interacting massless spin S particle, there are 2 theories, phi cubed theory and GR. Okay. So let me bring that one down. There's less to erase. So we see that the 3-point interactions are nailed, but all the constraints are going to come from writing down consistent 4-particle interactions. And we'll see what I mean by consistent in a second. So let's say we want to write down an amplitude for 4, 1, 2, 3, 4. And they all have spin S, but for fun, let me consider the 4-particle amplitude where 2 of them are minus and 2 of them are plus. Okay? Now, this is equal to 1, 2, 3, 4 to the power of 2s. Now let me call s little curly s here because I'll be using s for st and u in a second, times some function of s and t. We could write it as a function of st and u if we like, but remember s plus t plus u is 0. So it's really a function of just s and t. Okay? So what am I doing with this? I mean, I'm free to, this just defines f, right? So I'm free to factor out of the amplitude anything I want. I'm choosing to factor these guys out because this now completely accounts for all the helicities of the external particles, right? So these factors already give me all the weights that I need to match that amplitude. So whatever is left is only a function of the kinematic invariance, f of s, t, and u. So now we have to figure out what are the constraints on this function, f of s, t, and u. And there should be some constraints on it. There should be constraints because as I move around in the momenta of the external particles, at some point I can hit a configuration where, let's say, p1 plus p2 itself becomes null. So p1 plus p2 squared goes to 0. So what happens as p1 plus p2 squared goes to 0? So this is so it's the same as p1 dot p2 going to 0. It's what I was calling s goes to 0. Same name for all the same things. As s goes to 0, we know there's this primitive 3-particle interaction. So that means that this amplitude, by unitarity, f of st and u should have a pole when s goes to 0. So in the neighborhood of s goes to 0, it should go like 1 over s. But more than that, right in that neighborhood, as s is going to 0, what multiplies 1 over s, in order for it to have a correct unitary interpretation, what multiplies 1 over s has got to be the product of the 3-particle amplitude on one side and the 3-particle amplitude on the other side. Okay? More generally, if you have a big scattering amplitude, in the neighborhood of any pole, it needs to factorize into the product of what happened on one side and what happened on the other side. And that's reflecting the fact that you're making this physical on-shell particle, which is propagating from one side to the other. Okay? So this is where unitarity and locality, both, really, come in to say that f controls the pole structure of f of s, t, and u. And it tells us what I just said, that if I take this amplitude, that in this limit as s goes to 0, it needs to be 1, 2, 3, 4, and then I have to sum over everything that can possibly propagate there. Okay? So I have to sum over all the helicities. If that helicity there is h, this helicity here is minus h, so I have to sum. So this should go, as s goes to 0, to this thing times 1 over s, of course. So the coefficient of the pole, as it's blowing up, the way it's blowing up, the residue of the pole is given by the product of the lower amplitudes. Okay? Said another way, if someone hands you a random function f of st and u, and you go looking around and you find there's a pole in some random place, that pole has no physical interpretation, has no unitary, it would give you an imaginary part to the amplitude with no corresponding unitary interpretation for what the scattering process is. Okay. Now here too, I stress again, we're assuming a weak coupling. We're assuming that this is happening in some leading order approximation to what this amplitude is, and in that leading order approximation, the only possible behavior we can have as a function of st and u is to have poles. We know that if you start calculating loop corrections in field theories, in addition to poles, you can get logarithms in the amplitude, you get branch cuts, and it gets more interesting. So we're not talking about that. We're assuming, as we were yesterday, that this is in some leading order approximation of some weak coupling. So we're only assuming that it has poles. Okay. Okay, so let's do it. So let's first figure out what that constraint means on F a little more explicitly, and then we'll solve for the constraint. Okay, so let's actually, and by the way, it's not just S, right? It's S, any of the other channels I should be able to make the same argument for. We'll just focus on S, and I'll tell you what the result is for the other ones. It'll just follow by a symmetry. Okay, so let's see what happens precisely. Let's see what happens as we send S to 0. Now, remember S, which is P1 dot P2, is 1, 2, angle bracket 1, 2. And we're making everything, as I said before, everything is complex here. So I want to avoid a sort of trivial thing that can happen. You see, I have this power of 1, 2, 3, 4 outside. If I send 1, 2 to 0, I can just make that, if I send angle bracket 1, 2 to 0, I can sort of spuriously make the prefactor 0 and not get something interesting. So I'm going to do it by, I'm going to make this happen by sending square bracket 1, 2 to 0. Okay? If I send square bracket 1, 2 to 0, then, okay, P1 dot P2 is 0. And so this thing should factorize into a product like this, 1 minus 2 minus 3 plus 4 plus. But now, because of the angle bracket 1, 2 is 0, this amplitude, whatever it is, has got to be the minus minus plus amplitude, because that's the only one that we're putting in is the 3-particle amplitude. I should have said that I'm assuming that we're only putting in the minus minus plus interactions. It's a separate story if we put in the all minus interactions, but remember, those are these higher dimension operators. The things, they don't contribute in the leading approximation at low energy. So we're just looking at the leading interactions. Okay, so this is going to be the one up here. So this is some intermediate I, and there's I here again. And so this is, so here the helicity here has got to be minus. Okay? All right, so let's just write down what the 3-particle amplitudes have got to be on the left, on the top, and on the bottom here. So on the top, we have something that looks like 1, 2 cubed over 1 intermediate, 2 intermediate, to the power of the spin, S. And then on the bottom, it's the opposite around guy, so it's 3, 4 cubed over 3i, 4i to the power of S. And I should be getting a 1 over S in front of the whole thing. Okay, so that's what the amplitude needs to do. As S goes to 0, this amplitude needs to look like that. All right, let's simplify this guy a little bit. So this is 1, 2 cubed, 3, 4 cubed over. And now let me just let me do something that's going to make my life a little bit easier. Let me just notice that I can combine, for example, I have 1, so this 1i, 3i, I can also write as 1, and then the whole momentum pi, and 3. And the other one I can write as 2, and the whole momentum pi, and 4. This is all to the power of S. And I do this because this momentum pi is just equal to p1 plus p2, negative p1 plus p2. So because it's equal to negative p1 plus p2, the piece which is proportional to p1 let's see. I think I wanted to do it. I wanted to do it the other way around here. Oh no, that's yeah. No, that's perfectly fine. Sorry. Right. Yes.
What that power is outside the main bracket, I can't read it.
S. Yeah. This is the spin of the particle. Okay. Yeah. So this guy is just equal to 1, 2 times 2, 3. And this guy is equal to 2, 3 times 3, 4. Again, the reason is that I can replace pi. Pi is p1 plus p2. The piece with p1, when the lambda 1 part of the p1 contracts with the guy on the left, I get 0. So the only contribution I get is from the p2 part. And the p2 part, the 2 part contracts there to give me 1, 2. And the 2 tilde part contracts there to give me the angle brackets. And similarly on the other side. OK, so you see nicely these, what I end up getting is just 1, 2, 3, 4 to the power of 2s. And then what's left is this angle bracket 2, 3, square bracket 2, 3. That's p2 dot p3, which is also t. Okay? So what I get is t to the power of s. Okay? So that piece is t to the power of s, and then I have the overall 1 over s from here. All right. So that's what it must look like. Okay? As I approach this, these things are called factorization channels. So as I approach s goes to 0 in that factorization channel, the whole amplitude has to look like this. On the other hand, we've written down what the general structure of the amplitude is. The general structure of the amplitude is that 1, 2, 3, 4 to the 2s times some function of st and u. So you see the overall pieces that know about the helicities just cancel between the left and the right. And I learn an interesting constraint on this function of st and u. So let's write down what that constraint is. So the constraint is that as s goes to 0, f of st and u has to go like 1 over s, 1 over t to the 2s. Sorry, 1 over t to the s. Okay? So I told you it has to have a particular pole structure. This is a particular pole structure it has got to have. Okay? And so similarly, as t goes to 0 and as u goes to 0, those are the 3 different channels. It has to do all of the rest of them. So it's got to go like 1 over t, 1 over s to the s. I should have mentioned that as s goes to 0, t becomes equal to minus u. So, and all of these things are being raised to even powers, remember. So the signs don't matter here. I could write s here, for example, or u, and it doesn't make any difference because as t goes to 0, they're the same thing. Or I can have 1 over u, but here the structure of the pole does matter. I can have 1 over u, which is 1 over s plus t, okay, and then or 1 over minus s plus t, and then the thing that multiplies it has got to go like 1 over s or t. It doesn't matter. T to the s. Okay. So this is the structure that the answer. This is the structure this function f of st and u has got to have. Okay. So I hope the logic has been completely clear, right? We start writing the most general form that a 4-particle amplitude could have, and now we put in the physics of unitarity, physics of locality and unitarity, that the poles of this object, in the neighborhood of the poles, we have to be able to interpret as breaking up into the product of lower point amplitudes, and just phrasing that directly on this function that encodes all the non-trivial information of the amplitude tells us that it has to have this behavior. So now the problem is reduced to a math problem. Is it possible to find a function of two variables, s and t? Remember, u is dependent on s and t. Is it possible to find a function of two variables, f of s and t, such that it has those poles? The answer is yes if s equals 0 and s equals 2, and no otherwise. So let's see that. Okay? So the claim is that this is only possible for s equals 0 and 2. Let's actually write down the answers. Curly s equals 0 or 2. Okay? So when s equals 0, this f of st and u is just 1 over s plus 1 over t plus 1 over u. When s equals 2, f is 1 over stu, and that's it. Those are the only functions which satisfy this property. Let's just very quickly check and see that they do satisfy this property. Obviously, this one does. As s goes to 0, it goes like 1 over s, t to the power of nothing. So there's the 1 over s, and the 1 over t, and the 1 over u. And let's check this one. As s goes to 0, it should go like 1 over t squared. And it does, because as s goes to 0, it goes like 1 over tu. But remember, u is equal to minus t as s goes to 0. So it goes like 1 over t squared, indeed. Okay? Yes?
The scale case, the symmetry argument says the coefficient on the STU components.
Both symmetry, yes. And in fact, but it's all just baked into this. It's baked into that factorization requirement. It's all there. Okay, so not only are these the only cases, but as a bonus, we've actually worked out what the amplitudes are. Okay? So that is the 2 to 2 scattering amplitude for phi cube theory. That's a little bit trivial. You recognize just the simple propagators. But it's also the 2 to 2 scattering amplitude for gravitons. Just 1 over stu times this beautiful factor of angle bracket 1, 2, square bracket 3, 4 to the 4th. And this was a calculation. This is a hellish calculation if you use standard Feynman diagrams. That was done for the first time in the late 1960s, but it's a complete horror. And when Bryce DeWitt did the calculation and found this incredible answer, he suspected there was probably a better way of doing it. Okay? But here, we haven't stared at the GR Lagrangian. We haven't picked out any cubic terms, quartic terms, gauge fixed, nothing. We've just determined the answer completely just from consistency requirements. Okay, so let me. I started like 10 minutes late, so can I go for a? Let me just give you a sort of sketch of the argument. Well, it's not a sketch. We'll actually give. So how do you prove a statement like this? There's a very standard kind of. There's a very standard sort of method in this business. It looks a little bit complicated because it looks like you have a function of many complex variables, two complex variables, s and t, and you're trying to see if it has a particular kind of singularity structure. So, but a very useful fact that's useful over and over again is whenever it seems like you have a complicated problem with many variables, just choose one particular direction in which to explore the space of all the variables. Okay? And if just in that one direction we understand what all the poles are, then we can completely determine what the function is. Okay? So the idea is to consider not moving around totally generally in these two complex variables, but moving in a particular direction. So to do that, I'm going to introduce some variable z, and I'm going to look at a function, let me call it little f of z, which is big F at s plus some alpha z and t plus beta z. Okay? Now again, implicitly this means it would be u plus gamma z, where gamma is equal to negative alpha, negative beta. Okay? But again, it's just a function of s and t. Right? So s and t are fixed, but I'm introducing this deformation. And I'm going to look at this function of z, f of z, in the z-plane. All these things are complex, so I'm going to look at it in the complex z-plane. Now, there's a first important point here, which you can very easily check by dimensional analysis. By dimensional analysis, it's easy to see that this function s, t, and u, just if you go out at large, if you just homogeneously rescale s and t, okay? So let's say you just homogeneously rescale s and t to go to large values of s and t, this function has got to die as you go to infinity. So this capital F of s, t, and u, just by trivial dimensional analysis, dies at infinity. Okay? And this means that this function of z, you see at huge z, all I've done is basically replaced s and t by alpha times some big number and beta times some big number. Okay? So, and then I'm taking that big number to infinity, so this is just going to go to 0. Okay? So that's the first thing that we know. We know that f of z goes to 0 as z goes to infinity. Right? But also, by assumption, again, our assumption is that, I should have also said, not only is this the function, but these are the only poles that it has. Okay? So we're going to assume that this function exists. If that function exists, it tells us something about the poles of f of z. Let me write it here. I've been using this board all day. Okay. So in the z-plane, where am I going to have poles? I'm going to have poles when s plus alpha z is equal to 0, when t plus beta z is equal to 0, and where u plus gamma z is equal to 0. Okay? This is when s plus alpha z is equal to 0, t plus beta z equals 0, u plus gamma z equals 0. Okay? So those are its only poles by assumption, and it vanishes at infinity. Now, you remember from elementary complex analysis that if you know a function's, if you know all of its poles, you know it only has poles, you know all of its poles, and you know it vanishes at infinity, you can trivially reconstruct it from the knowledge of its residues at those poles. Okay? So that's just Cauchy's theorem. I like to call it Cauchy's theorem just to annoy my French friends, but enough of them have been annoyed that I'm going to go back to using the appropriate name for it. They actually get really annoyed. It's kind of funny. Stupid American, you don't know how to pronounce? Of course I know how to pronounce Cauchy. Who doesn't? Okay, so Cauchy's theorem, apart from sounding very pretentious, is very powerful. Okay, so if we look at the integral dz over z, f of z, and I do this as a contour integral around z equals 0, on the other hand, this is f at z equals 0. That's what we want, right? We actually want to know what this function is. Oh, I just erased it. But f of z is this f of s plus alpha z, t plus beta z, u plus gamma z. So on the one hand, I want f at z equals 0. But on the other hand, using Cauchy's theorem, I can take this little contour around here, and I can deform it to be the sum over the 3 circles around the other roots. Okay? So this is equal to the sum of the other residues, sum of the residues at the other 3 locations, right? Of 1 over z at the residue times the residue of f there. Okay. All right. Now let me not do the algebra. I mean, it's 3 lines of algebra, but maybe I'll leave that as part of your exercise. But I'll give you the answer. You see, we know exactly all of the residues. That's the whole point, right? We know precisely what this function looks like in the neighborhood of all these poles. It has to look like that. Okay. So we know exactly what the residues are, and therefore we know what the right-hand side is. And so we know what the function is. So we can completely determine this function. And this is what you find that it is for general S. Okay, so what we find is that f at 0, which is just the f that we want, is equal to the now it's going to naively depend on alpha, beta, and gamma. Of course, the whole function doesn't depend on alpha, beta, and gamma, right? So whatever answer we find, it better not actually depend on alpha, beta, and gamma. Alpha, beta, and gamma are some auxiliary construct that we've introduced to try to do the computation, but this is what we find. So this is exercise for you to verify, very simple, is that it's alpha to the s over s times 1 over alpha t minus beta s to the s plus beta of s over t, same, so yeah, let me factor it all out, actually. Result of little computation shows that. So this is, again, assuming that this function exists, this is what it would have to be. Okay? And now we're going to run into a contradiction. Unless s equals 0 or 2. Now let's say s equals 0. That's the simplest case. This funny factor isn't there. These things are just 1 over s plus 1 over t plus 1 over u, done. That's exactly what we said it was going to be. Okay? But for higher s, you see, there was a worry. For higher s, there's a worry because the only poles this function was supposed to have was when s and t and u go to 0, by assumption, and yet we constructed it, and here it has this other funny pole. It has this other funny pole at alpha t equals beta s. It's a total random, crappy spot. It even depends on alpha and beta. Okay? However, you can show very simply that uniquely when, oh, sorry, this is s minus 1. Make sure of that. Or maybe it's just s. No, it's just s. It's fine. Sorry. Yeah, it's just s. However, you can show uniquely for s equals 2 that that pole is spurious. So how can we check if this pole is really there? Well, I can see. Let me go to the neighborhood of when alpha t is equal to beta s, and let's just see if it blows up, right? But there is a prayer, because it could be that right in the neighborhood of alpha t equals beta s, these coefficients conspire to add up to 0. Okay? If they add up to 0, they put a 0 where the pole is, and you actually don't have a pole there, and then everything is fine. Okay? So that's all you do. You shove into the left-hand side what happens when alpha t equals beta s. You shove it in, and you find that uniquely, when the spin is equal to 2, does that spurious pole cancel. And furthermore, you find that the whole result is 1 over s to u. Okay? So when s equals 2, this thing becomes 1 over s to u. But if s is bigger than 2, there's a spurious pole there. And therefore, this object can't exist. We assume it existed. We constructed it from Cauchy's theorem. And then we found an object that violated the assumptions, contradiction. Okay? So that's the spirit of this sort of argument. Okay? You find the constraint for what kind of pole you're looking for. And then you explore the space of complex planes by doing a deformation, a simple one-dimensional deformation, just like we did here with one complex variable. And you use Cauchy's theorem to construct the object, and either it works or you find a contradiction. So this is just a little dumb complex analysis way of proving that no such function exists unless the spin is equal to 0 or 2. Okay? But I hope you see that this has a much more powerful feeling. It doesn't depend on, we want to write a Lagrangian using polarization vectors, this, that, and the other. It's just, there's simply no such function. Okay? Now, let me just take 2 minutes to just give you a survey of the other kinds of results that you can prove like this, some of which I've given as exercises. You can try all of them. They all work exactly the same way. So if you do the same exercise, this is one on your this is your problem set problem. If you do the same exercise with multiple spin 1 particles, and as we said, you have to put them in. You have to put the coefficient to be FABC. Then you put it in. You write the most general 4-particle coupling that you can, and you find that the only way that it can satisfy factorization is if the FABC satisfy the Jacobi identity, so that you've built the consistent interaction for Yang-Mills theory. And on top of that, you've computed the 2-to-2 scattering amplitude for gluons. Congratulations. Okay? You can do the same exercise for. You can try to do the same thing for multiple spin 2 particles. Okay? If you do the same exercise for multiple spin 2 particles, so let's say we're going to have many spin 2 ABC. We make this coupling, I don't know, call it GABC. Then you find that instead of the Jacobi identity, you have to have the following similar looking but not exactly the same identity true. Something like GA1, A4, C, G, C, A3, A2, minus G, A1, A3, C, G, C, A2, A4 has got to equal 0. Okay, so the Jacobi identity has 3 terms. Here you find this funny 2-term identity has got to be true. And then this is a little bit more work, but it's not so hard, to prove that the only solutions of that can be diagonalized to be put in the form of multiple non-interacting spin 2 particles. Okay? So you can't have any non-trivial interactions between them. Okay? Another example that you can do, another very nice example, is to look at the interaction of massless spin s particles This is the last one I'll mention, and then I'll stop. So you can't have more than one. You can't have more than one graviton. Now let's say we want to imagine spin s particles interacting with gravity. So here we have to decide. So if we call the particle, I don't know, phi. So we have phi 1, phi 2. So we want to imagine writing down this kind of cubic interaction with the graviton. And we have to decide what kind of interaction that we can have. This is another tiny exercise for you to do, is that if you put in the interaction where 2 of these are minus and that guy's plus, again, we know what the interactions are, but this has different units than 1 over m Planck. Okay, so that's not the appropriate interaction. The appropriate interaction is phi 1 minus phi 2 plus and the graviton. So that's 3. So this could be minus or plus. Let's say it's minus or plus. We could have either one. Okay? So this has units of m Planck of 1 over m Planck. So this is what we should mean by the gravitational interaction. And actually, physically, what this means is that the interaction, all the momenta are incoming here. Okay? So, but if you think about phi 1 coming along, emitting a graviton, and then moving along, it says that the interaction with gravity isn't switching the helicity. Okay? So it's reasonably the leading interaction. And yeah, it has different and higher units than 1 over m Planck. So this is the leading interaction again. Okay? And so let's say we give it a coefficient c. It has the same units. Let's say it's c over m Planck. Then you do the following exercise. First, you look at the consistent factorization. You look at consistency of the scattering amplitude for just for this new particle, phi 1 minus, phi 2 plus, phi 3 minus, phi 4 plus. Okay? Just like we did for the other one. If you look at consistency of that, and it factorizes, and precisely the same argument, precisely the same kind of complex analysis, you find that this is only consistent for spin 0, a half, 1, and 3 halves. And then starting at 2 and higher, it's impossible. And it's a very, again, the logical structure is identical and the abstraction is identical. You construct a function, it has spurious singularities, and you find that the spurious singularities are not there except in these cases. Actually, if you're going to do this yourself, if you literally want to follow this argument, to make life simpler where the thing vanishes in infinity, it vanishes in infinity only for 1.5, for 1 and higher. Okay? So you need a slightly different argument for 0.5. But anyway, those are the less exciting cases. Starting at spin 1 and higher, it trivially vanishes infinity just by dimensional analysis. And if you just follow literally what I told you, you'll find it's very similar. You remember here, there are 2 cases, s equals 0, where there was trivially no spurious pole, and s equals 2, where there was potentially a spurious pole, but it canceled magically. Exactly the same thing happens here. At s equals 1, there's trivially no spurious pole, and at s equals 3/2, there's a potential spurious pole, but it cancels magically. Okay? And okay, these theories all have names, including the very last one, which is, of course, just supergravity, just the interaction of a massless gravitino with the gravitons. But it tells you there's no consistent interaction for higher spin particles. So remember I was telling you yesterday that purely from the point of Weinberg's theorem and all this stuff, you could very easily imagine having higher spin particles. Sure, they wouldn't mediate inverse square law forces and so on, but you could imagine having higher spin particles. They can have self-interactions. You can build all of these things, provided you, if you're going to write down a Lagrangian, you build everything out of the linearized, for example, if it's massless spin 2, you could build it out of the linearized R mu alpha beta, or the higher spin analogs. And all that's perfectly fine without gravity, but with gravity you can't do it. Okay? And this is one way directly of seeing that you can't do it. If you're going to try to play with the Lagrangian, you discover you can't do it because in order to make these things invariant in this trivial way, we have to give it interactions purely built out of these linearized Riemanns and their friends. And coupling to gravity makes it impossible to maintain that gauge redundancy. It's very simple. It's relatively simple to see. So you can see these things from a Lagrangian point of view as well, of course. But again, it's a very, very invariant way of thinking about it. So that's what you get from consistency of this amplitude. This argument doesn't tell you what C should be. So you then look at the consistency of the 1 minus 2 plus graviton 3 minus graviton 4 plus, and that tells you that C has got to equal 1. So the interaction of this guy with gravity has got to, it respects the principle of equivalence, just like all the other things that we've said. Okay? And anyway, so you can explore anything your heart desires, the consistency of any funny theory you might imagine that your heart desires by following exactly the same procedure. So this unfortunately took me 2 lectures when I thought it would take me 1. But I hope you've seen now from many points of view this basic deep fact that theories of massless spin 1 particles and higher, certainly massless spin 1 and massless spin 2 particles, are incredibly constrained. Their dominant low energy interactions are nailed by general principles, just Poincare invariance and unitarity. If you want to describe them in a Lagrangian formalism, you must use a gauge redundancy. And again, if you're just talking about these degrees of freedom and nothing else, it's very difficult to make sure that that's all you're talking about. And doing it even with the aid of, writing down Lagrangians for it with the aid of gauge redundancies uniquely nails what the Lagrangian should look like. The amplitudes are uniquely nailed. Again, all its leading approximation at large distances. So that gives us the backdrop on which to now imagine what modifications of these theories at large distances might look like. And it tells us the little wiggle room we have for modification. In fact, the bottom line is that every modification of gravity that's remotely concrete and makes any sense and has any equations associated with it at all Even if in the beginning it looks like some very magical, crazy thing with extra dimensions and brains up the wazoo and this, that, and the other, in the end of the day, it's just adding some dumb extra degrees of freedom. And typically, they're scalar degrees of freedom. Because if there's no other degrees of freedom, we're done. There's nothing else that we can do. This is the long-distance theory, period. Okay? And so no matter how strange or fancy it looks, in the end of the day, it's just always adding boring or less boring scalar degrees of freedom. And so that's what we'll start talking about tomorrow.